Dear audience and students, we will continue on the interaction between the radio waves and the human body or biological tissues. The maximum permissible exposure limits for mixed frequency fields. Maximum permissible exposure limits are the highest fields or radiation power densities that should not be exceeded when exposure of a human being to wave is considered. Mixed frequency fields means that we have many sources of radio waves surrounding us, and sources have different frequencies. So how can we calculate the exposure? If it is one frequency, then we just take the expression or value from the table. But if we have different frequencies, we use this equation here. Summation from I equal 1 to n. N is the number, n is the number of sources at different frequencies affecting us or exposing us to radiation. Si is the exposure to each frequency, the exposure level or exposure value, exposure radiation density from each frequency, and Li is the limit, the maximum allowed at this frequency. Their summation should not exceed 1. S1 is the exposure, actual exposure or calculated exposure from frequency 1, and L1 is the maximum allowable limit of exposure taken from the tables or from the regulations, and S2 is the actual exposure or calculated exposure at frequency 2, and L2 is the limit, maximum limit allowed by the regulations, and so on. Again, we stress the fact here that unfortunately the regulations consider only the thermal effects. The non-thermal or athermal effects, which are important, are not considered. Only temperature increase is considered. Here is an example on how to use the mixed frequency fields to calculate the maximum permissible exposure limit, and to see if it is less than 1 or greater than 1. Consider this example. We have radio wave fields or electromagnetic fields at a location which exposes the location to the radiation from 4 antennas. The first antenna, let's call this is first antenna. Okay, the first radiates 33 volt per meter at the site considered at the frequency of 18.1 megahertz, and the second antenna or the second source exposes the place to 20 volt per meter at 47 megahertz, and the third antenna, the third source, radiates 15 volt per meter at the site, or the radiation from the antenna reaches 15 volt per meter at the site considered at 152 megahertz, and finally, this is just an example of course, and finally the actual numbers may be much higher than that. And finally the fourth antenna exposes the location to 1 volt per meter electric field at the frequency of 460 megahertz. Now we need to calculate the exposure level. Okay, using the Federal Communication Commission limits. The limits, since were published, were not significantly changed. It were not significantly affected or modified, I mean, unfortunately. Now we want to see the limits here. We can see this is the 1996, but the current limits did not change. This is just how to calculate, only how to calculate. We have, you can see the power density here for 3 to 30 megahertz for occupational. We said that occupational or controlled means that people who know the effects and who can exercise control over their environment to reduce the radiation levels. The limit is 900 over the frequency squared in megahertz. And for 30 to 300 megahertz, the limit is 1. It's fixed, 1 milliwatt per centimeter squared. And for 300 to 1500 megahertz, the limit is the frequency in megahertz over 300. This is occupational. For population, general public or uncontrolled environment, the limit is for 1.34 to 30 megahertz is here. It is 180 over the frequency squared, plane wave equivalent power density in milliwatt per centimeter squared. And for the frequency range of 30 to 300 megahertz, the limit is 0.2 milliwatt per centimeter squared. For the range from 300 to 1500 megahertz, the limit is the frequency in megahertz over 1500. Above that, the limit is fixed. It is 1 milliwatt per centimeter squared. We were here, okay. Now let's calculate. Here at 18.1 megahertz lies between 1 point for controlled environment, occupational. It lies between 3 and 30 megahertz, where the limit is 900 over f, the frequency squared. It's 900 over the frequency squared. This is f. F is 18.1. The result is 900 divided by the frequency 18.1 squared, and the result is equal to, as you can see, 2.747 milliwatt per centimeter squared. The second frequency is 47 megahertz, that lies between 30 and 300 megahertz, where the limit was 1. It was fixed 1 milliwatt per centimeter squared. And similarly for 152, it lies also between 30 and 300, so the limit is fixed 1 milliwatt per centimeter squared. The fourth frequency is 460. It lies between 300 and 1500, and the limit is frequency over 300. Frequency is 460 divided by 300, and we will obtain 1.53. As you can see, it's 1.53, milliwatt per centimeter squared. Now we want to calculate those are the exposure limits. Now the exposure values, the radiation density values. It is given by the equation 0.1 the electric field squared over the wave free space or atmospheric wave impedance, which is 377 ohms. This is ohm. And this is the electric field. This is the E field magnitude. Okay. So for the first value, it is 333. So we multiply 33 squared times 0.1 over the impedance, wave impedance. We obtain here, let's see, it is 0.1 times 33 squared divided by 377. We obtain 0.288, it's approximately 0.29 milliwatt per centimeter. For the 20 volt, we put here the electric field is 20 volt. From here it is 20 volt. It is 20 squared times 0.1 over 377. 20 squared times 0.1 over 377, and this is equal 0.106. As you can see here, it's 0.106. The third one is 15 squared 0.1 times 15 squared divided by 377, and this is equal to 0.06, 0.0596. It's approximately 0.06. The last one, is only 1 volt per meter. Here it's 1, here it's 1 times 0.1, it's 0.1 over 377. 0.1 over 3 divided by 377 ohms, and the result is here it is 2.7 10 to minus 4. This is 2.7 10 to minus 4. Okay. Now we plug in these values into the above equation here, to this equation. We divide S by L and sum, and see if the summation is less than 1, which is acceptable according to the regulations or guidelines, or not acceptable. Well, remember that only thermal effects are considered or taken into account. The radiation here is 0.29 and the limit is 2.747. We divide, and the radiation is 0.106, and here the limit is 1, and the radiation here is 0.06 and the limit again is 1, and the radiation here for the final value is 0.00027, and the radiation limit is 1.53. When you sum these values, you will obtain 0.27. You can see here 0.29 divided by 2.747 plus 0.106 plus 0.06 plus 0.113027 divided by 1.53, close the bracket, and we will obtain it is 0.27. Here it is 0.27, and 0.27 is less than 1. Therefore, according to the regulations, it is acceptable. To find the limit for uncontrolled environment, we need to repeat the calculations. The exposure will be the same, but the limits will be different. Let's see here. Let's read this text here. international acknowledgement of the risks associated with electromagnetic energy. Now, in 2001, the International Agency for Research on Cancer announced that the extremely low frequency fields that involve the fields of the electrical power net, all the fields of the electrical power net at 50 Hz, at 60 Hz, at below this 300 Hz, are possibly carcinogenic to humans. 10 years later, in 2011, and specifically on 31 May 2011, the International Agency for Research on Cancer, which is part or associated with the World Health Organization, announced that the radio frequency radiations of cell phones and other equipment, also radio frequency radiations, are possibly carcinogenic to humans. Okay. We will see this non-thermal effect. This is an example of non-thermal effects. This was a research paper on non-thermal effects, percentage of exposed inhabitants under or near mobile base station tower. This means that the mobile tower, and control group. There was the people under study that they live near the cellular tower or base station, and another control group living 2 kilometers away where there is no tower. And we compare here the behavioral complaints. Now the complaint, the exposed here, the headache. 23.5% of the exposed group that they live near the tower complain of headaches, whereas only 10% of the people who are living far away from the antenna or the tower, they complain of headaches. So the increase might be associated with the proximity to towers, living near towers, of course, sleeping. Now, memory changes. 28.2% of the people living near towers suffer from memory changes, whereas only 5% of the people living away from the tower suffer from memory changes. Dizziness. 18.8% suffer from dizziness. 18.8% of the people living near tower, the cellular tower, suffer from dizziness, whereas only 5% who are living away suffer from dizziness. Tremors. 9.4% of the people living near towers suffer from or has complaints of tremors, whereas no one living away from the tower suffer from the from the tremor. No one has tremor out of the people living away from the tower. Depressive symptoms. 21.7% of the people living near the tower suffer from depressive symptoms, whereas only 8.8%, lower percentage, of the people living away from the tower suffer from the depressive symptoms. Also, only 10% of the people living away from the tower suffer from the sleep disturbance, whereas higher percentage of 23.5% of the people living near towers suffer from the sleep disturbance. This is also another study comparing the people working in TV broadcasting stations and radio broadcasting stations. Now this is here percentage of the operators with hypertension, high blood pressure. So the people working in radio broadcasting stations and exposed to the radio frequency radiation, 60.8% of the workers have hypertension. And also similarly, people working in TV broadcasting stations and exposed to radio frequency radiations, 59% of those workers suffer from hypertension, from the people who are exposed to radio frequency radiation. Whereas people working in the TV and radio and are not exposed to radio frequency radiation, only 29.1% of these people suffer from hypertension. You can see that almost double the percentage. The people exposed have double percentage of the hypertension as compared with the people not exposed. Also the hearing loss here, the hearing loss. Mean values of hearing threshold for right and left ears of exposed group working and living at broadcasting station and control group did not work with radio frequency sources. So people exposed to radio frequency sources at broadcasting stations, their threshold value, dB, hearing loss, is 26.4, whereas the control group is only at 4 kHz is 13.2. Higher threshold means that the person will need louder voice to hear. Lower threshold means the person can hear lower amplitude voices. So the people exposed are adversely affected. Also at 8 kHz, the exposed group to electromagnetic waves, to radio frequency radiations at broadcasting stations, have a threshold loss of dB 28.8 dB, whereas the control group who are not exposed have dBHL of 20. So here they need higher levels of voice and sound to hear. Here they do not. They need lower level to hear. Oh, this is just an example. Here an example of how to calculate the thermal effects temperature increase. Since the human body is mostly made of water, around 3/4 of the human body is water, we consider here examples in water. How much energy is absorbed by a kilogram of water with conductivity of 1 Siemens per meter if an electric field of 500 volt per meter is impressed for a period of 600 seconds? And what's the maximum possible temperature rise if the 1 calorie is 4.186,055 joules? Now from this equation here, SAR, specific absorption rates, equals sigma E squared over rho. Sigma conductivity is 1 Siemens per meter and the electric field is 500 volts per meter, and rho, the mass density of the water, is 1000 kilograms per meter cubed, 1 ton per meter cubed. Now we calculate this. Let's see, 500 squared divided by 1000 equal 250 watts per kilogram. Now the power, this is watt per kilogram, so the power is equal the SAR times the mass, because this is watt per mass. Multiply by mass, you will obtain the watt. The mass is 1 kilogram, a kilogram. So we multiply by 1. The result is 250 watts. The energy is the power times the time duration. The power is 250 watt and the time is 600 seconds. Therefore 250 times 600, we obtain the energy is 150,000 joules. Now I want to calculate the temperature increase. We use this equation. SAR is equal C delta T over T. C specific heat of water or of the tissues, and delta T temperature increase, and T is the time period. Now SAR, we have already calculated SAR. We know SAR. SAR is known, and is given, it is constant for water, and T, the time period, is known. We calculate the temperature increase or possible temperature increase. So delta T is equal SAR times T over C. SAR is 250, as you can see from here. Here 250, SAR is 250. And the time duration is 600 seconds given in the question. And the specific heat for water is, as you can see here, it's 4.18 joule per gram. If you want per kilogram, we multiply by 1000, so it will be 4186 for 1 kilogram, because we are using kilograms here, not grams. So 4186.055. And if you multiply these together, you will obtain here 250 times 600 divided by 4186.055 equal 35.8 degrees. This is the possible temperature rise. If the temperature of water is 64, then it can increase by 36 to reach 100, because the maximum temperature of water is 100 degrees. After that it starts to boil. If the original temperature of water is 80 centigrade, the increase would be only to 1 centigrade. It will not be 35.8 centigrade. Consider another example. How much energy is absorbed by a quarter kilogram? Quarter kilogram is 250 grams of water at 20 centigrade in a microwave oven cavity that delivers 700 watts for 200 seconds. And 1 kilogram calorie is 1 over 860 kilowatt hour, which is 4186 joule. We can just show this. Kilowatt is 1000 watts times hour is 3600 seconds divided by 860, and this is equal to, as you can see, 4186 joule. 4186 joule. Okay, to find the power, the energy, the power is given 700 watts. We multiply by the time. The time is 200. The time is given, I think, I remember how much energy is for 200 seconds. Yes, here it is, 200 seconds. We multiply by the time, 700 from here. We multiply the power by the time, we obtain the energy. 7 times 2, 14, and we put the 4 zeros. Now to calculate the temperature rise, we use SAR. SAR is equal power over mass. Power is 700 and mass is 250 gram, which is a quarter kilogram, 0.25. 4 times 700 is 2800 watt per kilogram. And this equals C delta T over T. C is 4186, specific heat for the water, and delta T is unknown, and the time period is 200 seconds. From this equation we can find delta T is 133.78. This is possible temperature rise. Of course the water cannot increase by this amount because the maximum is 100, but this is the calculation. To find the impressed electric field, we use this equation. SAR is known now, 2800. It's equal sigma E squared over rho. Sigma is given here. Sigma is 1.23 Siemens per meter. Sigma, and E squared is unknown, and rho is the mass density of water, 1000 kilogram per meter cubed. From this equation, we can, from this here, you can multiply this or this, and the result is here. Let me calculate it. 2800 times 1000 equal divided by 1.23 under square root. The result E is 1508 or 1509. 1509 volt per meter. Here you can see it is the same value. Here 1508.8, so 1509 volt per meter. Another problem here, a half kilogram of water initially at 25 centigrades just begins to boil after 240 seconds, which is 4 minutes. 4 minutes is 240 seconds in a microwave oven if the heat of evaporation of water is 539 calorie per gram. Estimate the microwave oven power. Now for a period of 4 minutes 240 seconds, the temperature was 250 centigrade initial temperature, and it starts to boil. Begins to boil means that the temperature is 100. So the temperature difference delta T is 100 minus 25 is 75 centigrades increase. We can use SAR here also. SAR is equal power per mass. Okay. The mass is half kilogram, as we said. Power is unknown, and C is known for 186 for water, and delta T is 75. We already calculated that, and the time is 240 seconds. From this we can find the power. Here you can see the power is equal 0.5 times 4186 times 75 divided by 240, and we obtain 654 watts for the microwave oven. This is the rating, power rating for the microwave. And that's all for now. Thank you for listening. If you have any question, comment, please let me know, and meet you at another session. Thank you. Thank you for listening.